Okay, folks, is it working? Okay, I'm not sure I can hear well. I think it should be working. So today I would like to start first video as an introduction to Frost. Where Frost is a scheme to create threshold signatures compatible with Schnorr. So that's very interesting in the context of zcash, which does not have multi-signature or threshold signatures, and this would allow us to add this functionality to zcash or anything that is similar to zcash. So before, as the purpose of this first video is not to go into the details of Frost, because it's quite complicated. I can't say I understand completely, to be honest. But just to see from a very high level what it allows us to do, and what's the purpose of this stuff. So before we actually even, so the target audience of this video is people who are interested in digital signatures, public key encryption, all this stuff, without having too much exposure to these concepts before. So essentially, it's very low bar. You're not supposed to do. You don't have to know very much. So I would start with very basic concepts, and the first one is concept of, I would say, call it identity. So one of the main things that you would have in this thing is that you want to be, something that other people don't know. Right, so in many cases, for example, when you want to spend some money and you want to prove the ownership of an address, people give you send you bigger coins to a particular location, to a particular address, and you want to show that you are the one who knows who created this address, and you have some knowledge that other people do not have. And in cryptography and public key cryptography, this knowledge is represented by a value, an integer. So it's essentially like if you have a very, very large number of balls, of items. So in this case, it's like any number you can pick any number you want. Right? So there's a game where you simply pick a number between 0 and 100, and people try to guess that number. But instead of being 100, of course, in our case, the number is going to be extremely large. It's going to be 10 to the power 77, 80. Let's say something like that. So it's not exactly that number, but it's around that range. So that's like 1 followed by 80 zeros. So how many zeros is that? 3, 6, 9, 10, and 4, 5, 6, 7, 8. Right, that's that number. And that number is very difficult to comprehend. But as a comparison, it's probably higher than the number of atoms in the universe. So if you pick one of these numbers between 0 and that guy, it's extremely unlikely that somebody else would have picked the same number if you really randomly choose numbers. And once you have that particular choice, that's going to be your secret. So you don't your secret, I'll call it secret, is in 0 and that number, that range. So not exactly that, but around that. And now there's a process, there's something that allows you to convert between that secret and a public value. So that's your secret key. And then you can have a public key that is a function. So you take of the secret. So basically you take the secret key and you can transform that into a public key. And that process is fairly fast, very well known, but very hard to reverse. So that's the key. That's a very important property. Is that if you have a public key, it is not computationally possible to find a secret key. So going from secret key is to public key is okay, is easy, but going from public key to secret key is impossible. I mean, again, impossible is to the best of our knowledge. So maybe someday somebody would be able to crack this algorithm. By the way, it's called elliptical curve cryptography. The software we're using, cryptography. But it's actually a very general term, so we don't even need to know that to remember that it's called elliptic curve cryptography. All we have to know is that there's some way to go from secret to public, but not the other way around. So we can write it maybe in easier way this way. Okay. But that way, impossible. Okay. So basically, this is like if you look at stars in the universe, you can go from every star had a label, a secret label. You can pick a number, and then that will associate to a star, even more than that, right? And then you can show that star, that public key, and say this is mine, right? And the reason why it's yours is because you know the secret key that matches it. If somebody else goes and says, no, it's mine, it's my public key, you can always say, okay, I challenge you. If it's really yours, prove it to me by showing the secret key. So here your identity is your public key. So you can pass this around. So some people write it on their business card. There are servers where you can register your public key associated with an email address. But the point here is that you need to have a way to say that public key, that particular value here, is yours, and you can create as many public keys as you want. The only thing is that there has to be some way to say that that public key is yours. And then afterwards, if we are going to talk about how you prove that you actually know that you are the person that has the knowledge of the secret without actually giving a secret, right? So that's the second step. So that's actually going to be very close to the end. The digital signature. And the process here is, well, you claim that you know the public key. You claim that this is your public key, and the only difference between you and somebody else is that you have the knowledge of the secret key. So the most obvious way to show that you know the secret key is, okay, show it. Right? So if you reveal the secret key, then people can verify that that secret key by using the same process as here. Right? You detect the secret key that you reveal. They derive the public key that matches it, and they compare it with the one that you say you have, and that's the match. It means that yeah, you do know the secret key. Right? So that's the obvious way to show your identity. But that will only work one time, because once you reveal it, the guy who checked your identity now has your secret key, and nothing prevents him from impersonating you by showing the secret key to the next person, and so on and so forth. So, and very soon, everybody will know your secret key, and the value associated with your identity is gone, because anybody who has access, whether it's the first person or second, third, and any number of person who can now copy your secret key, because it's just a number. And any of these people, we have the same knowledge as you, right? So that's actually really bad. Right? So the idea of a digital signature is to show that you know the secret key, but without giving that information to the person that receives the proof, right? So not sure, right? So prove you know the secret key without revealing it. Right? So that's the biggest magical part of it. And furthermore, it's even better than that, because what we can see is that you will be able to do that while revealing it specifically for a certain message. So there's a third component involved here, which is the message, a message. Right. So in if we talk about like what you would do in real life when you sign something, so whether you sign a check or you sign a contract, your signature on the contract is going to be the same one, right? Whether the contract is saying is a lease for a house, or whether it's a contract for buying a car, the contract will be vastly different, but your signature will be the same. And obviously your signature is not going to be the same signature as somebody else. But what I'm saying here is that your signature will be identical regardless of the message. That's not the case for a digital signature. For a digital signature, so the digital signature is going to be specific. So let's call it sig of. So sig is the signing function, right? So you're going to sign a given message, and then you're going to sign with your secret. So this process, signing will be a function that takes a message as an input and your secret. And this provides a digital signature. And the idea here is that if the message changes, or if you have obviously a different secret, the output digital signature will be different. Somebody who receives that digital signature, so the inverse, not inverse, but the companion algorithm would be verify. So verify takes the digital signature. So the purpose of the verification function is to make sure that you are really the person who has signed that message. So it obviously takes the signature. It also takes the message, because we said that it depends on the message. The signature depends on the message. But this time it doesn't take the secret, because the guy who receives the signature does not know the secret. He knows your identity, so he knows the public key. And so this function verify should have an outcome of either true when everything is okay, or false if there's a forgery, if something is not okay. And the thing that can be not okay could be any of these three terms. So for example, if the person tries to modify the message, so you sign a message, a contract, but somebody tries to modify that message. For example, the message was a contract for a car, and you agreed on the price, or you agreed on a particular model, and somebody tries to cheat and increase the price. So the message will be different, and the verification routine will return false. So that's one example. Second example is obviously if the digital signature is a forgery, so it's not the result of this signing function. So again, the verification will fail. And finally, if the message is authentic, the digital signature is also authentic, but it was signed by somebody else, so that public key does not match that secret key, then again, it's going to be a failure. So these two algorithms put together allows you to show that you know the secret key and that the message has not been tampered. So that's even more than what we want. And obviously we have to add one thing, is that getting the digital signature will not allow the recipient, so that's the second person, this is you do that, and they do that, right? They verify. So the person who receives the digital signature, the message, and knows your public key should not be able to figure out the secret. So there's a zero knowledge aspect to it. So that's the point of a digital signature. And there are various schemes there are various ways to implement this sign and verify functions. One of the most popular ones were invented by a guy called Schnorr. And these kind of signatures are used a lot, for practically everywhere. So they are used in, so now they're not used in Bitcoin yet, but now they are going to be used in Bitcoin. They're used in zcash, etc. Lot of cryptocurrencies are using Schnorr signatures. So again, this doesn't have to be. This is just one way to create, to implement the signing and the verification algorithms. But it's a very popular one. And the purpose of Frost. Right, so let's go. So now we'll go back to the main point. For Schnorr, you're dealing with one key pair. All right, so the identity is the secret key and this public key. Now, in some scenarios, you want to deal with, you want to have more than one participant, one person. So with Schnorr, since you have one secret key and public key, one person knows the secret key, and therefore he will be able to create a signature. So one person can sign. So there are scenarios where trusting the entire knowledge to one person is too risky. And we're talking now about threshold signatures. So these are schemes where instead of having one pair, like this, so one person actually, that's the main characteristic, is that you would have n participants, n persons, right? Or they usually call participants, but let's call it n persons. So you have n persons, And you have another parameter which is called threshold t, so t lower than n or equal, so lower or equal. And the threshold, let's call it like this, but remember it's equal possible, or t equal n. And the idea is that each person has one part of the secret, right? So they call it one share, but that's the same as one part of the secret. And if they want to create a signature, one person by himself will not be typically capable of creating the signature, as he will not be able to run this algorithm all by himself unless t equal 1. So you need at least t people. Sorry. And one of the interesting things is that t doesn't have to be n. So let's say you have 3 people only, and you have t equal 2. That means that any 2 people out of the 3 people, so any 2 participants out of 3, would be able to together would be able to create a signature. Of course, if you have 3 people, is even better, but 1 is not enough, and obviously 0 is not enough. And once they go together, they will be able to create a signature like this one, this digital signature, that anybody can verify using the Schnorr method. So what we change in Frost, we change 2 things. We change the signing algorithm changes, and we change the key gen. So let's talk about key gen a bit later. No change in verify. So that's a very powerful argument here, because it means that the logic in cryptocurrencies, nodes usually play the role of verifiers. They verify that the transactions are correct and reject anything that does not obey the protocol rules. So they actually only run the verify part. By saying that with Frost you don't have to change the verify algorithm, means that the protocol does not have to change, and therefore you don't have to deploy new code or anything. So as far as the rest of the system is concerned, so obviously the people who are participating in the signing part algorithm or signing protocol will be aware that they are using Frost. But once the signature is produced, the verifiers see that signature as a valid Schnorr signature, and they use the same algorithm as before. Right. So that's the part where Frost affects signing, but it also affects key generation. Right. So why does it affect key generation? When we think about it, it's fairly very obvious. If the key generation was not affected by Frost, it would mean that one person is able to generate the key, right? The public key, and well, it could be desirable. It could be, but it has the drawback that if he generates the public key and he knows the secret key that is associated with that public key, nothing prevents him from pretending to have given shares to other people, but in fact he has also kept the original secret key, and he then has a backdoor into the system. He's able to produce signatures all by himself because he has the secret key, and he doesn't have to go through the new signing protocol. So we need to change. Frost needs to change that keygen into an algorithm that distributes the generation of the key, the public key, among all these participants. So that's called DKG, right? Distributed key generation. That's DKG. So in the DKG scheme, all these n participants will each provide a part of the secret. So they each have a secret, but one person by himself is not going to decide the final secret. So actually altogether they provide one piece, and the outcome of that DKG will be a public key. So that's the group public key. Altogether they have this group public key, but none of the people actually know the secret key. Right, so we can write it as the outcome of DKG is the group public key. All right, so everybody will agree on that same public key. So when you distribute the public key, you will actually distribute this group public key, and each participant, each person has a share, a secret share. So the secret share is such that if you have T people out of N, they can use their secret share to create a signature. So it is improvement between quotes over the previous algorithm, where signing we're using a message and a secret. Right, that was the previous sign. Where's sign? Right, message and secret. Now it's going to be a message and the secret shares together. So we have sign, take, and the message, and a certain number of secret shares, at least T of them, and this will create the digital signature. So actually that part should be done first, obviously. And the verification is the same as before, so it's going to be a verification on the message, on the digital signature. Right, so this is a digital signature, and this time on the group public key. Right, so this at very high level, this is what Frost is going to give us. So that's, I think, enough for this time, and if we are going to get into more details about this part here and then this part here in the next video. So I hope it was helpful, and I see you around for the next part.